Hello everyone. Let's analyze. So let's look at these two strange objects at the top of the screen. The square root of 1 plus the square root of 1 plus the square root of 1 plus. It goes on for a while. In fact, the dot 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 indicates it goes on forever. Or the other strange object, 1 plus 1 over 1 plus 1 over 1 plus 1 over 1 plus. You get the idea. The dot 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 suggests something infinite is happening. But what exactly is happening? Can we say that this is equal to something if it never ends? And when we say it's equal to something, what do we mean? On the very first day, we talked about the square root of 2, and we talked about we can use different algorithms to get a number that's ever more closer to the square root of 2. But can we say that we actually get to the square root of 2? What does it mean if I were to say that the square root of 2 is a limit of the sequences I talked about in the first lecture? Well, it turns out that these two things do equal to a finite number, and it's specifically the golden ratio, 1 plus the square root of 5 over 2. How do we know? And how could we prove such a thing? And how could we build up a machinery to talk rigorously about what it means when a sequence converges as it approaches infinity to a number? Why else do we want to think about such things? Well, consider the world of applied mathematics, where we're trying to solve differential equations or integral equations or matrix equations, and often we either cannot or don't want to solve these problems analytically because it's too expensive or not possible. So what we would like to do is to build an approximation, and usually these approximations are indexed by something. Sometimes n, where n corresponds to some discretization number, or a number of quadrature points for integration. But we would like to show that as n goes to infinity, our approximate solution converges to the actual solution in order to legitimize the approach that we're taking. And of course, if we know that that happens, then sometimes we would like to say at which n do we get close enough if I can get arbitrarily close. Okay, so what is a sequence? We all have an idea of what a sequence is. We can think about it two different ways. One is a function from the naturals to the reals. Okay, it's essentially a rule, right, that defines for every natural number, 1, 2, 3, 4, and on, a real number. Of course, another way of thinking about the same object is a list of real numbers that's indexed by the natural numbers. If it's indexed by all of the natural numbers, or if it's a mapping of all of the natural numbers onto R, then that necessarily means that it is an infinite list. So for example, let's consider the sequence 1, 1/2, a third, a fourth, a fifth. The sequence whose nth entry is 1 over n. Okay, so this would be a sequence we index by n. The function, right, that defines the nth entry is 1 over n. So we can think of it as a list, we can think of it as a function. So what do we mean when we say a function, or I'm sorry, a sequence converges to a limit? Well, a sequence converges to a limit if, and only if, for any epsilon greater than 0, there is a natural number that guarantees that every sequence entry for index larger than that natural number minus the limit is less than epsilon. Since epsilon is arbitrarily, what we're saying is our sequence is arbitrarily close to the limit L. And it's arbitrarily close for every single entry in the sequence that's larger than some finite n. So as an example, the sequence 1 over 1, 1 over 2, 1 over 3 that we talked about prior, it should be no surprise to anyone watching this that this converges to 0. But how can we show that 0 satisfies the definition of a limit given above? Well, to show that, we would need to show that for any arbitrary positive epsilon, there is a big N, that's a natural number, that would guarantee that 1 over n minus the limit, which is 0, an absolute value, is less than my arbitrary epsilon for every single n bigger than big N. Okay. Well, our goal is actually equivalent to saying for an arbitrary epsilon, show that 1 over n can be made less than it for every n bigger than some natural number big N. In plain language, that means 1 over n can be made arbitrarily small or arbitrarily close to 0. Okay. So this method of proving a result in some sense is a bit of walking backwards. It's stating what your goal is. In other words, we want to show that 0 satisfies the definition of the limit. So we state what the definition of the limit is for this sequence with the limit 0. We state it and we say, well, that's equivalent to this problem. And then we kind of walk backwards towards something that we know. Well, what do we know? We know, and we've proven in the textbook, that the set of natural numbers is unbounded. There is no largest natural number. So, for any positive epsilon, 1 over epsilon is a number, right? It's the multiplicative inverse that we're guaranteed to exist because of the field axioms. So we know 1 over epsilon is a number, and there's a natural number bigger than it. Because if there wasn't, 1 over epsilon would be an upper bound on the set of naturals, which we know does not exist. So there's some natural number bigger than 1 over epsilon. Okay. Well, if 1 over epsilon is less than big N, okay, then that would imply that 1 over n is less than epsilon. And for any n greater than big N, 1 over n is also less than epsilon. Well, that's exactly our goal, right? We just show that for all n greater than this big N, which of course depends on epsilon, 1 over n is less than epsilon, right? And again, it's true for every single n bigger than that natural number big N. Right? So again, since epsilon was arbitrary, right, an arbitrary positive number, we've proven our goal. Okay. So just like for the definition of the supremum and the infimum, we're going to give a alternate definition of what it means for a sequence to converge to a limit L. And in order to get to that, we need to define what a neighborhood is. Okay? It's a term that we're going to use often in this class. Okay? So a set U of real numbers is a neighborhood of X if U contains an open interval that contains X. Okay? So for example, the interval 0 to 1 is a neighborhood of 2/3. Why is it a neighborhood of 2/3? Well, the interval 0 to 1 contains the open interval of 2/3 minus 1/1000 and 2/3 plus 1/1000. In fact, the interval 0 to 1 contains the interval 2/3 minus epsilon, 2/3 plus epsilon for every epsilon bigger than 0 and greater and less than or equal to 1/3. So for example, if I had the closed interval 0 to 1, that's also a neighborhood of 2/3, but it's not a neighborhood of 1 because the closed interval 0 to 1 does not contain an open neighborhood that contains 1. Sometimes it's useful to specify a neighborhood of a particular size. So rather than say a neighborhood, we might specifically say an epsilon neighborhood. When we say an epsilon neighborhood, what we mean is the interval x minus epsilon to x plus epsilon. We also might call that an epsilon ball around x. Of course, it doesn't look much like a ball since we're in 1 dimensions. Okay, so this theorem will offer to us an alternate definition of a limit. When I say an alternate definition, right, why is it marked theorem and not a definition? Well, it's marked as a theorem because we have a definition, and we're going to prove is that if a limit satisfies the definition, it also satisfies the theorem. And if a limit satisfies the theorem, it also satisfies the definition. So the theorem says that the sequence an converges to a limit L if and only if, which makes it an alternate definition, every neighborhood of L contains all but a finite number of sequence entries. So since this is an if and only if statement, we have to prove both directions. We have to prove that if L is a limit by the original definition, that implies that every neighborhood of L contains all but a finite number of elements. We also have to prove that if every single neighborhood of L contains all but a finite number of sequence entries, then L in fact must satisfy the original definition of a limit. So let's start with the for definition. Suppose an converges to L. Well then, by definition, it means for any arbitrary positive epsilon, there is a natural number big N. And for every n bigger than or greater than big N, an is arbitrarily close to L. In other words, an minus L is less than epsilon. Okay. So if we remember from the last lecture on absolute values, the absolute value of an minus L being less than epsilon is equivalent to an minus L being sandwiched by negative epsilon and positive epsilon. We can add L to both sides of both inequalities, and that would imply that L minus epsilon is less than an, which is less than L plus epsilon. And that, in fact, is the definition of the open epsilon neighborhood around L. In other words, that means an is in the open interval from L minus epsilon to L plus epsilon. The key is that this is true for an infinite amount of n values, because there's an infinite amount of n values that are bigger than or equal to the natural number big N. And since epsilon is arbitrary, we showed that every neighborhood of L, right, because every single neighborhood of L contains some interval L minus epsilon to L plus epsilon, which contains every single entry of an for n bigger than big N. So we just show that every neighborhood of L, right, there is an n for which all sequence entries except for a subset of a1 through an are contained in it. Right? We know that an for all n bigger than big N is contained in the neighborhood, and of course some of the sequence entries might also be in this neighborhood, right? But some subset, right? The neighborhood contains all entries except for some subset of a1 through a big N. All right, now let's prove it the other way. Assume that every neighborhood of L contains all but a finite number of entries. Well, then in particular, we know that for any epsilon, right, because if any neighborhood, then that includes any epsilon neighborhood, Right? So for any epsilon, the epsilon neighborhood of an, the epsilon neighborhood of L contains every entry of an except for some finite subset. So let's let n be the largest index of that subset, right? The subset not included. Okay? Right, remember, every entry of an is in an epsilon neighborhood except for a finite amount, right? So because I have a finite set, it has a largest index, and we're going to let n be the largest index of the subset not included. Okay? Well, if n is the largest index of the set not included, then for every little n bigger than that big N, we know that an is in the epsilon neighborhood. And well, if an is in the epsilon neighborhood of L, an is less than L plus epsilon and greater than L minus epsilon. Subtracting L from every side of both inequalities means an minus L is sandwiched between negative epsilon and epsilon, which, according to our theorem on absolute values, implies that the absolute value of an minus L is less than epsilon. Epsilon is arbitrary, and that's true for all little n greater than big N, which is exactly the definition of L being a limit of a convergent sequence. And that proves our result. I'll see you next time.